I would say, is this theorem, which is theorem 2, and was theorem 2, which helps us to estimate the error of the approximations. So this is the equation, a little bit more general than the one which we will apply to. And this is the estimate here, which we want to prove. And I started the proof with, for the case m equals 0. So m, I remind you that m can be any non-negative integer. So the case m equals 0, then we use Ito's formula for the L2 norm of the solution which we know exists, because this equation is just an equation in L2, so a Hilbert space. So we can apply Ito's formula as well. From Ito's formula, we relatively easily get to this inequality using the stochastic parabolicity condition. This kappa is from the stochastic parabolicity condition. So we had this inequality, and then we took expectation, killing the stochastic part. In fact, one should be more careful. One should use localizing arguments, a sequence of stopping times. But if one is even more careful, then one can notice that this is not necessary, because one can also use that the solution of the SDE has those estimates which ensures us that in fact this is a martingale. The argument is the same which Professor Kulob showed you, using Davis inequality, and then one can check that this is a martingale. But if one doesn't have that estimate, then one can use a stopping time argument in order to kill this, and then after taking the expectation, so everywhere one gets the estimate for the expectation of this by Grunwald inequality. In fact, when one applies Grunwald inequality, one also should be careful that the right-hand side is finite. So again, two possibilities: either using stopping times, to making them finite, and then and applying Grunwald in that case, and then using Fatu's lemma, or again we check that in fact it is finite when we use. So I suppose, even though I haven't explained well, but I suppose that everyone is familiar how to use German. So therefore that, Grunwald's inequality, so therefore we now know that this part until capital T is estimated like, so this part is estimated by that what we want, even this as well, but we want more. We want to have the supremum to be estimated, and here again, in fact, I repeat the calculations which you have already seen in the lecture of Krylov. So these calculations are just the same. So what we need to do now, we go back to this inequality. So here, and then we take the supremum in time until capital T. So supremum, or rather just until it's T, because again Grunwald will be used. So ut h squared, and that is less than or equal to u naught squared, then this part until capital T, but But, okay, let us find that down. Plus this, oops, here one can take until capital T. I have already taken in fact. So before, okay, that's fine. And the stochastic integral and so on takes the supremum of the stochastic integral. As R, let's say dWr, where SR is written here, so from Ito's formula, this is there, so summation with respect to rho. We take expectation. And this part has already been estimated like that, so it is not interesting. So that is just constant times what is here. So the only new thing to estimate is this one, right? And so here absolute value, or sorry, not absolute value, are what I have. Yes, absolute value. What we have here is then the absolute value of that one, and so the URH, and here the inner product in L2 in Ito's formula. So H rho plus G rho, and we use Cauchy inequality, Cauchy-Bunyakovsky inequality, and take out the supremum after that in time. So here, this one, and with expectation is less than or equal than expectation. Oops, I need first I should use, sorry, what I'm doing. First I should use Davis inequality in order to estimate the supremum, and that, so we deal with this term now. Let's say R. So R is less than or equal than 3 times. This is by Davis inequality, as you have already learned from the lecture of Coulomb. So 3 times expectation and integral from 0 to t, and S rho r squared. So that means this squared U R H M H rho r plus G r rho inner product squared d dr, and and square root of it. That is also 2. So therefore this is in fact 6. And now we take out. But to estimate this part, one takes out the first Hölder inequality, Cauchy-Bunyakovsky inequality, and then one takes out the supremum. So this is less than or equal than a constant expectation supremum less than or equal to t u r h this 0 norm, and integral from 0 to t, and the m r h rho plus g r rho dr, and the whole thing is square root. Now here there is a summation. Yes, here there is a summation. So this summation remains here with respect to rho. And now one uses Gyong inequality with small constant such that it is less than or equal than 1/2 the expectation supremum u.
Let's go to the here.
Sorry?
No, the UH are scared.
So big bracket may be moved to the right a little bit.
Only right, yeah.
The right, sorry? So this,
Okay, in that case, I think the absolute value of UHR square.
this is the, no, because there is, oh sorry, yes, there is the square root, right? So when one takes out so here, one takes out the square of it with the supremum from the integral, but then the square root, so therefore this is what.
Just parenthesis alone. Parenthesis you should move between. So big bracket.
Also, this premium in your parentheses.
The square root, so the square root is before taking the expectation, right? Okay, and then sorry, now I understood. Sorry for that, yeah. So otherwise the square, okay, sorry. And now by Gyong inequality, this is square supremum. Now the square with a small coefficient plus big coefficient expectation, and some integral from 0 to p m r h rho plus g rho r dr. And this one we have already estimated, because that part is just so let's see this from 0 to t, that is the b alpha rho and delta alpha h alpha, oops, the UH disappeared, from the writing and everywhere else. So UH and plus the GR. So this dr. So obviously this is less than or equal, then take the 2 square of it, so twice expectation integral from 0 to t. This is bounded, and so what we can estimate this by, there is also a summation here with respect to alpha, so one can estimate this by summation with respect to alpha and delta h alpha UH squared plus twice expectation, so dr plus twice expectation and gr rho square dr. Now this we have estimated in the first step with the quantity we want. This one also on the right hand side of our estimate. Obviously we can take that until capital T, until capital T. So this is all right, and then we put this onto the other side, checking that this is finite, and that we get from the result from the estimate for the SDE one way of doing it, or the other way, if we wouldn't know that, then by stopping time, we use stopping time. So first we stop the UHR norm process, which is continuous, such that it becomes bounded. Then we do that, and then Fatou's lemma. In fact, we see that here no other Bellman is necessary, so I could have written the whole thing until capital T. We got that estimate. Is that all right?
Excuse me. How do you take care of the integral of USH on the right hand side?
On the right hand side,
No.
Not
The
here.
first line.
first line. This one.
Yeah.
Ah, yes. So this one, in fact, has already been done, right? Because, for example, when we estimated also from in the first step, we can estimate two things, right? This one, and also the expectation of this one for each t. So in the first step, we can estimate that even the supremum of the USH, sorry. Oh no, that's fine. So expectation USH 0 squared supremum in S with respect to t. It is estimated also by the right hand side by n times square t. Once we have that estimate, then for the integral, that's always the case, in fact, that when you have the estimate already from Bellman for the function itself, then obviously you have an estimate for the integral as well, but then the capital, another dependence on capital T. Right. So I suppose I have done the estimate in the case m equals 0. Is that all right? Then the next step is now that m greater than or equal to 1. And to get this, we take the derivative of the equation. This is a usual method in these that one would like to have estimates for the derivatives. So this means m derivatives should be estimated in L2. Let us do, for simplicity, just the first case when m equals 1. So, and fix one direction, so fix the I derivation, so derivation in the direction of EI. So what we do, we take the derivative of the equation, so apply dI to the equation, let us call it equation H. Now, this is not just a formal argument now. We can do that because don't forget that we have the fact that the u, we know that the UH is a continuous process with values in HM, right? So the UH process has M generalized derivatives in L2. So that means we can take, how can we take that? A simple way of explaining how can we take that this equation, just we use test functions and we write the meaning of the equation with test functions. That is the same, and in order to do that rigorously, let us use test functions which are from C0 infinity, and in fact let us take like this, that di is minus di. So we apply the test function minus di phi, which is again C0 infinity, and then we use integration by parts. So you imagine what I'm saying here, yes? That when I use test function, that means everywhere we have the test function. We choose this test function minus di phi, and then we drop the derivation onto the other one. Then we have the equation for every test function, C0 infinity test function, phi. And so that means we have the equation for the derivative, right? So we have the equation for the derivative. Is that all right? So to make the writing easier, let us use the notation phi tilde denotes di phi. Now this phi is not just a test function, any function, so I use psi, is a notation that for any function which appears, if we take the derivative, we denote it by tilde to write a bit shorter. So okay, so we have then the equation by applying this derivation. We have this equation u tilde ht equals, now once the derivation comes onto a, but that we write later, let us write the one which appears here. So that means we have the delta minus h beta, a alpha beta, and the delta h alpha uh tilde, plus I write here f chapeau, and I give it in a moment, plus the d alpha delta h alpha u tilde th plus g chapeau dwt. So where, okay, the initial condition is just the derivative, where the f chapeau equals, so when we take the derivative here, yes, so that means the delta, oops, maybe it's better, sorry, excuse me, I make just to have a, this is where you notice that it is better. What is the advantage here to use this? So I write delta, I write this part here as delta minus h and beta in this way, because you will see that that is convenient. This is why we use the form of the equation like that. So in that case, when we take the derivative, then the derivative comes here. So the f chapeau is then the a tilde and alpha beta and delta h alpha u dh plus, when we take the derivative of this one, so plus the f tilde beta. And then for g t similarly, then we have the b tilde alpha delta h alpha u dh plus the g t tilde. Is that all right? Is it? Yes. Okay. And then we just apply now from here, apply the case m equals 0, because now our equation is in the form as the original equation, just with new data, new initial condition and new free terms. So we know then that we have this estimate. Maybe I write here now with tilde, and okay, here we don't know yet exactly, but let us just put a bar and then just check the bar, which is now the expectation in the u tilde 0 squared plus expectation integral from 0 to t, and the f chapeau beta, or just I don't write now the betas, that means plus the g chapeau 0 squared dt. And now look at this. How can we estimate? So that part is not interesting in fact. And then plus here, this is by our assumption, m is now greater than or equal to 1. So therefore the derivative is bounded, so that we can take out the constant. Pardon, the constant is lost already here. So and then the estimate L2 known of this. So sum delta H alpha ut H L2 known squared over alpha and plus the f tilde beta. Also when we take the square back from here, that is already the previous, and what else? Plus similarly from here we get a term like this, right? With the 0 we have the that is written also here, so we can just write that estimated by plus and the k, okay, not k, because we have the derivative, so sorry, but like this. Alright, k, not the 0 but the 1. So when this m means that the data is derivative m up to m times, and we take the L2 known. So is it all right? And this one here is estimated. So we got the estimate for m equals 1. And we see that one can go further, so precisely an induction is made. So that's, in this way we can easily do the induction. So this is the way how one can explain. So I think that then this is proved. Is it accepted that this estimate is proved? Right? Okay. Then let us apply now this estimate. So theorem 2 is applied to the equation for, so theorem 2 the equation for the VH, which is the U bar H minus U. This is the finite difference scheme solution, but in the L2 sense. We saw this is why the bar is there, and the equation, you remember, is this one, LH, the H plus the F, which is the L, LH minus L on U, the T plus the integral, oops, what I'm writing, plus the MH U, VH plus the MH minus M on UH dW. Right, this is what we denoted earlier by FH. This, but oops, important that this is not the UH but the original solution, the true solution, and this is the GH. And now we from here know that if we are interested in the supremum of the VH, let's say L, now L norm squared, then from that estimate we know that that is less than or equal than the initial value norm of it, but the initial value is 0, so then this term n times expectation integral of FH squared plus GH squared dt, but L, sorry, L and dt, right, using by theorem 2. So one needs to estimate these terms. So we just notice that the FHL is less than or equal than an n constant. So this is, I remind you, the WL norm or HL norm of this is less than or equal than a constant times the U, and here this is a second order, and so it will be L plus 3. We can check that, and for GH we can estimate it by the L2 norm of U, and times the L2 norm of U, L norm is by the L plus 2 norm. So first let me put here a star, and we will check this if we have enough time. So suppose I am right with this, okay, then what we get is the following, that so let us write it as theorem 3, that let A1 until A3 through A3 hold with M greater than or equal than L plus 2, then we have the estimate for the VH supremum in L squared is less than or equal than, oops, what I'm saying, here you believe that is true what I have written here, but not good enough. There is also an H here, so this is coming. So there is here a difference of these two operators. They must be close to each other, and this is where an H comes out. So we should check this out, and then we get that this is n times H squared and Km T, and that I used, I think, the notation K squared for in the original one. Sometimes I left the square, doesn't really matter, but to have the homogeneity somehow it's better to, the notation is better if you use the square. So, okay, if we get that, and here, from here we can finish by showing, which is another task, by showing that in fact the UH, so here remains, it remains to show that the U bar H is the same as the UH. Though it was considered in L2 sense solution, in L2 sense, in fact, it is the same as in little L2 sense. So these two tasks remain. So let me deal then with this, the first star and then the two stars. So I suppose. Oh, wait. Maybe I haven't explained this. It might not be clear why we have now this. Why? Because notice, so the theorem 3 follows from what we have done, but maybe it is not completely clear. So I should remind you that what we see here is that in the L plus 3 norm, we have an estimate for the free terms of the equation. And an integral in the integral sense. If we have in the integral sense in L plus 3 for the free terms, then we have in fact in the L plus 3, let me check, it seems to be, yeah, L plus 3, okay, in that's fine, L plus 3, then, so maybe I write it down, so we have for the integral at dt, or maybe here, so that from here it follows that I have in the L plus here, I will go, no, it follows, I'm afraid, that only, so L plus 3 here, that means I don't have better, so unfortunately it is L plus 3, so then in fact I should have for M L plus 3 here. I made a mistake with the calculation, so if the free term has estimates in the L plus 3, then I have this in the L norm, this estimate, so then I should in fact require to have M greater than or equal to L plus 3 in order to get the estimate here in the L norm. So, right, so I made a mistake. It's good that I have checked. So we have this. It remains to check now that the U bar is the same as the U, and this
So is your solution on grid? UH is solution on grid?
yes, thank you. So the UH is the L2 valued solution, so solution on grid. On the GH, and this one is the capital L2 valued on the whole space RD. So different notions of solution, one would expect that these are the same, and that is really so. If M is greater than or equal to dimension half, so in fact here what is the 2 star when M is greater than the dimension half, because then we can talk about the L2 solution, and then we can also talk about the, so that was always an assumption, but now in order to get maybe one more, the final theorem to formulate, and then I will talk about the 2 star. To show the final theorem is that let A1 to A3 hold with M greater than L plus 3. Somehow I am now a bit shocked that I made this mistake with the 3, because I calculated capital many times and always 2, but something now not okay, but L plus C, and assume that L is greater than D half, then from this estimate,
I think L plus 2 there was just equal to.
or you can take, oh sorry, greater than or equal, not to be so, right, greater than or equal, then because this norm, the L norm, the Savoyard norm, dominates the supremum norm and also the little L2 norm, we can then estimate that it is that in the supremum over the grid, the U bar H minus the U squared is less than or equal than H squared times the K T squared, and also because of the embedding which we have seen as a lemma, this L2 norm little L2 norm is less than or equal by, and there is a constant which I usually forget to write. So that's it. That is the final thing with the with this remain to show that these two are the same. And so this is a little exercise that these two are the same, so I can get rid of this. For this we, again, kind of standard. You can find this technique in papers by Kurov, the kind of thing which we do in order. This is when in the SPD theory one talks about the generalized solution and the classical solution, and when one would like to show that a generalized solution, if the equation has smooth data, in fact the classical solution, just the same thing is done, which I am now showing. So we take, so modifying is what we do. We take now the function fix first an element from the grid. So this is fixed, and take phi, which is smooth, non-negative, and has a unit integral, and consider phi epsilon of y as y minus x over epsilon, and use the test, use this function as a test function for every epsilon for the equation for u. So that means we write u bar h and phi epsilon inner product in R2 equals u bar 0, which is in fact the u naught, but phi epsilon plus integral from 0 to t LH UH bar plus f phi epsilon inner product ds plus integral.
Because we're doing definition of phi epsilon is what?
Sorry?
We should put epsilon to minus. You gotta multiply epsilon to the minus.
No, sorry, yeah. Thank you. Then epsilon to the minus d should be normalized. Yes, thank you very much. Right. So this, and then here u bar h, g, oops, no, plus g, and phi epsilon dw. And now take epsilon to 0, and then it is easy to check using the convergence improbability criteria for the stochastic integrals for fixed t. X is also fixed, that improbability, this part converges to u bar h t at x, because this is a modifier, and we know that also this is a continuous function in x also L2 interval. So it converges to this one, this converges to U naught X plus, and then we got that LHU bar H S X plus F X. Remember, F is also continuous because we discussed that it is continuous, so converges to that one, ES, and the stochastic integral converges as well. So that means that almost surely this is satisfied for each t and for each x. Now we know that it is in fact continuous. There is a continuous version in time. So therefore, what we know that almost surely for all t, for that fixed x, we have only countably many x, so almost surely for all t and for all x on the grid. So this satisfies the equation on the grid for every x. Also, we know that this is little L2 valued. We know because of the lemma which first or second day I showed, the embedding of the WM2 into little L2. So when M is greater than D hat. So therefore this is an little L2 valued solution of the equation, but because of the uniqueness of the little L2 solution, we got that the U bar H is the little L2 solution. Right? So it is finished. Is that? So no question. All right. So I should admit that. So first of all, this appears in this paper as a very special case, and in fact we consider that in non-divergence form the equation. But the main aim for the paper is to go to the accelerated scheme, so this is how I would like to continue. But one more remark that this result by a different approach is obtained by Q, whom I already mentioned in his thesis. He used different method, also very interesting, and I like that, and it is a natural way to consider in the L2 theory these schemes. So what he did was that he considered discrete Sobolev spaces. So maybe one word about that. So just as the classical Sobolev spaces, one can define the discrete Sobolev spaces. Let's say, so the first one is the little L2, which we have already introduced, but we can also consider, let's say I put here an H, that means little L2, that for that we fix a grid and consider functions on the grid, like so functions on the grid with the analogous norm, so the norm of the function, let's say phi or psi, in this 2h, let's say squared, is instead of the integral, the summation, right? Summation for all. Let us denote gamma multi-indices less than or equal m, and then delta, let's say I write and h, and and I write multi-indices also gamma and psi squared and then h to the d. What do I mean under that? That we take so gamma, the multi-index gamma is gamma 1 and so on, gamma d, and the gamma is from 0 to 1 and so on d, and then when I write then the delta h gamma is then delta h and gamma oops, then this corresponds to the 0 if I
Gamma I is from
gamma, okay, gamma, no, I, gamma I, or rather, I should have written gamma to have that notation, gamma 0, and then I write gamma, okay, gamma I would take also inside. Alright, I do not make it more complicated. Let us just take from 1 to d, and then just like gamma I, delta h I, so just like the usual notation, and then if I don't take maybe the zero length corresponds to the operator, the identity, or just I would add the psi, and then also the summation over the grid. So this square x, and then x h to the d summation over the grid. So just the analogous thing, instead of taking the derivatives, one takes the, let's say, forward derivatives, find forward finite differences in the same way. Instead of the integral, one sums over the grid multiplied weighted by h to the d. And then using these spaces just in the same way and using the L2 theory, he gets the result he gets the estimate in Sobolev, discrete Sobolev spaces, and then from there, using embedding, he gets for the supreme. But then, in this way, there are two embeddings, one after the other, and for each, one needs the index must be the number of derivatives must be higher than d plus d over 2, so then it requires more. So maybe this approach is better when one considers on the whole space. And I would like to also mention that this kind of approach was used in papers by Kulov, and that for the breakthrough results on estimates, rate of convergence estimates for the fully nonlinear PDEs, the Hammond equation. So among very nice ideas, but so that idea is to consider the finite difference being not just on the grid but the whole space can have many advantages. Okay, so let me now go to the accelerated scheme or schemes. So that is
Why don't you use a different?
yeah. So an old idea of Richardson. So Richardson, the other word is Richardson extrapolation. So Richardson LF, Louise. Richardson, about 100 years ago, had the idea when he wanted to calculate, and he did that by hand, to calculate solutions approximately of PDEs, then by using finite difference method. Then he wanted to improve the accuracy, and then he sought to use the approximation on different grids, so grids with different mesh sizes embedded, and then from the two, taking a mixture to get a better solution. The idea behind this that one may have an expansion for u, h, let us say when one has a parameter involved in the approximation procedure, it might be that the approximation depends nicely on that parameter, in our case on h, so nicely that one can have, let's say, an expansion. So suppose that the UHTX can be written as the U, the original, so the true solution, plus, and then H and times U1 TX plus and so on, H squared U2 TX until, let's say, K, and one has then the H to the K TX plus some error term which is A of order HK plus 1, and here R which depends on H TX. So suppose that we have this, let's say in our case on the grid, with some functions U1 and so on UK independent of H, and the remainder depends on H, or can depend, obviously depends, and that can be estimated, so that is bounded. Say R H TX is bounded by some constant. So in other words, suppose we have a Taylor expansion of that. So maybe to make it more similar, we can also write this one. In that case, one can find, then suppose we have that, then if we take if we consider the following numbers B0, B1, and so on, Bk, defined as 1, 0, 0, is used of the Vandermonde determinant inverse acting on this vector defines that, where the Vandermonde matrix is defined as 2 to the minus I j, I minus 1, j minus 1, for I equals, so this matrix should, yes, from 1 to k plus 1, so a k plus 1 matrix. So suppose we define this and consider the UH, let's say, chapeau, as the linear combinations of the solution corresponding to different mesh sizes. So here B, oops, I put like this, okay, BI, and then UH over 2 to the I, so we always take the half of the mesh size. So we have the grid, okay, just in one dimension, then this is for fixed age, then we take half of it, so the middle points, again the middle points, and so on. So we have an embedded nested sequence of grids. Then we calculate the solution and this corresponding to the grid with mesh size h over 2 to the I, take with this coefficient, and then we take it from 0 to k. Then it turns out that once
H is about
sorry,
the index H of the electric in the bottom.
here
Yeah, location of H is different.
this age is the fixed age, but then we take half of it, and we take so we start with
solution, right?
sorry.
That's UH, right?
Yeah, oops, but I usually, yes, I change my notation, so I write here the H as a supper index, so that therefore I want to denote this, and that denotes the solution of the approximation corresponding to the H over 2I parameter. Right? Then it turns out that the approximation is much better, so that means that we take this minus the original, then in the norm which we are interested in, so let's say the supremum norm in T, and so this x means now that we take the supremum over T and over x on the grid, that this is less than or equal than n times h to the k plus 1 times the script T once. So this is the result, in fact, that oops, I mixed up now the two things. Let us assume that we have, then we can get such a better result. Why? Because just these are specially chosen coefficients, which when we take the mixture, all the lower order, all these terms are killed, and just the mixture of the remainder with this remains. So let's see this in the special case when we take just 2. So we have the UH, which equals the U plus H times U1 plus the A square and the R H. Yes. Plus, let us take the U with H over 2, which is U plus H half then. So this is true for every H, this expansion. These are the functions U1, U2, UK are independent, so here I have the same U1 plus the HK plus 1 and RH to the half, but that doesn't matter because this is bounded. And now it is clear that if we take twice the UH half and minus the UH, then when the first order in H term disappears, so we get the second order one, so then and this function is bounded, and therefore we have that this x norm then is less than or equal than n times now H squared. Okay, so this is, in other words, this is an important or good thing to have an expansion once we have an approximation. And so the next thing I would like to talk, but my time is just about ending, that to show quickly what we have learned so far gives us a quick way, relatively quick way, to show that such an expansion holds if the A1, A3 are satisfied with m greater than k plus 3 plus d half. And this is why I here wrote in that case, what we have here is k m t. So suppose m is large enough, then we have the better, essentially better, and as much smoothness we have, the more smoothness we have, the better approximation we can make.
So the norm in capital X refers to the supremum over the t of the grid points.
Yeah,
So you
two things. To the refers to supremum in time, and the grid points also refers to supremum in time and little r to norm over the grid.
the grid points with the step size h, not the smaller sizes. I mean, I wonder which grid.
Very good, thank you, very important question. Yes, they are on the original grid. We consider them on the original grid. So, yes, because this mixture should be understood, right? So then we should fix one grid where we consider, and the roughest, so the original one with mesh side H is considered when I talk about this X norm, but one takes the finer and finer grids in order to calculate these ones and then take the mixture. I don't have a computer experiment, but in some examples where one can calculate precisely the approximation and the original, the true solution, then indeed dramatically.
But we do have an example.
Yes, we do have, but we haven't run on computer.
Just computed explicit.
Yes, we computed explicitly those.
Better
And-
computer, but explicitly.
And fantastically better than one. So it is. I have the data, but maybe on the notes which I will produce, and will give, you can find the data. So that's all. Thank you for your attention. Time, so minus obviously the u, and then so this is my UH bar, the mixture, and minus the U, thank you. Otherwise that is nonsense. And here the X, that's